this is lecture number 11. And let's start by finishing up the example on waveguide that we started last time, at the end of last lecture. Remember, we were discussing the rectangular waveguide. Okay? And we're interested in the TE wave. TE stands for transverse electric wave. That means that the X component, this is the X direction of propagation. The X component of the electric field E is 0. So then we say that we are left with only the equation for Bx to solve, which you remember is function of yz. And to do that, as you recall, we adopted the method of separation of variables. Write this function, which depends on two variables, as product of two functions, each of which depends only on one of the coordinates. And then we plug in, and then we realize that there's 1 over y d squared y by dy squared got to be a constant. Similarly, this got to be a constant. And we call these two constants to be minus ky squared minus kz squared, minus for the reason that otherwise you will not be able to obey satisfy the boundary conditions. So let me copy this down. And last time we saw that the solution is of this form, namely Bx is yz after constant given by product of two cosine functions. One depends on y, the other one depends on z. Or m and n are non-negative integers. So that we are interested in solving. We have solved already for Bx, and we got k here. If I recopy this equation, that will tell me that k squared is equal to cos the other side, omega squared over c squared minus ky squared. Ky squared is this, is m pi over a squared minus kz squared. Kz squared is square of this minus n pi over b squared. So that k would be equal to square root of omega squared over c squared minus this m pi over a squared plus n pi over b squared. And let me actually put out this factor of 1 over c, so 1 over c squared, so that it comes out as 1 over c, so that I have to multiply this by c squared. Let me call this combination to be omega with integers labeled by the two integers m, n. M has to do with the larger dimension, which is a in this example, and n has to do with the smaller dimension, the width, which is b, is less than the height a. When we have solved for Bx of this form, we said that we are talking about the T, E, M, and mode of the wave. With the wave number being related to the frequency omega, like this. So that k is equal to 1 over c square root of omega squared minus omega sub m n squared, where omega mn is given by this. Obviously, for omega less than this omega m n, this will be negative inside the square root. So the k will be imaginary. The imaginary k corresponds to an attenuated wave, no propagation. So that in order to have this mn mode, you need the frequency to be greater than omega mn. Omega mn came here. All right? So let's continue, wrap up the discussion on this example. I can erase this now. K is given by this. Then obviously, okay, now I can take a look at omega over k, which, as you recall, is the phase velocity of this electromagnetic wave, v phase. What's that equal to? That's equal to c goes up, omega divided by square of omega square minus omega mn, omega mn. And we are assuming that omega mn is less than omega. Otherwise there will be no propagation of the wave. But you can see plainly that this will pour a factor of c. Numerator is omega. Denominator is square of omega minus this omega mn squared. This obviously is less than omega. That means that, in fact, this is greater than 1 times c. So greater than speed of light in vacuum. Well, normally we would be worried, but as you may remember, we talked about phase velocity last time. It is okay for phase velocity to be greater than speed of light and still be okay, because we know that energy and accordingly also information got transported with a speed not given by the phase velocity, but the group velocity. So what's the group velocity for this example? Group velocity, you remember, is d omega by dk. Since I have just given k in terms of omega, so let me in fact put this as reciprocal of dk over d omega. And what's that equal to? Well, that is obviously c goes upstairs. Derivative of this is 1/2. Cancel that with the 1, so that it is 1 over square root of omega square minus omega mn square. Take a derivative, so there's 2 omega, so there's omega. Which, of course, is c times square root of omega square minus omega mn square over omega. And obviously, the numerator is less than omega. So that the group velocity for this example, obviously, is group less than speed of light in vacuum. Hallelujah. That's good. That's fine. No problem. With special relativity, which sets the bound speed of light in vacuum c as the maximum velocity of propagation. All right. So much for discussion on waveguide. And now we are ready to start the main thing in this lecture 11, number 11. And now let me erase all this. Let's start on the discussion of electromagnetic wave. Oh, let's see. What did I call this topic? All right, electromagnetic radiation. It's a very interesting topic. And to do that, let me in fact start the whole thing by telling you a technique which we are going to use to discuss this topic, electromagnetic radiation. And that technique is known as Green's function technique. Green's function technique. This technique was introduced by George Green, born in 1793. He worked out the three-dimensional case for a three-dimensional Green's function case in 1828. And 11 years later, in 1839, he solved a four-dimensional case. And one of the most devoted students of the Green's function technique was my late thesis advisor, Julian Schwinger. Julian Schwinger was a master of this technique. And in fact, he used this technique to do his work in quantum field theory and QED, quantum electrodynamics. And you remember that his work on QED won him a share of the Nobel Prize. In 1993, 2 centuries after the birth of George Green, there was a meeting in Nottingham University in England. Nottingham University was the home, where George Green was. So there was a bicentennial celebration of his birth, and Schwinger was invited there to receive an honorary degree. And of course, he was asked to give a talk. And the title of Schwinger's talk was The Greening of Quantum Field Theory, George and I. And it was a very interesting talk. And in case I just recall that you have never seen the picture of Julian Schwinger, this is what Schwinger looked like. And I edited a book in his memory. In 1995. This is Schwinger. So the title of my book is Julian Schwinger, the physicist, the teacher, and the man. And if you have a chance, you can check out this book from the library and take a look. Right? It's very simple. Well, it's a very interesting book to me at least. So he gave this talk in 1993, and unfortunately, shortly afterwards, he was diagnosed with pancreatic cancer, and he passed away the next year in 1994. In the spring of 1995, I organized a section in the APS meeting in Washington, D.C., and this was a result of the meeting. All right, so what I'm going to tell you is the approach adopted by Schwinger in solving Green's function. And let me give you a physical motivation first, why we are interested in using Green's function techniques to do this electromagnetic radiation problem. Well, let me first of all remind you that in the Lorentz gauge, divergence A plus 1 of C squared del V by del T is 0. In this gauge, the potential and the vector potential in terms of which you can write down the electric field E and magnetic field B right away. the differential equation for V and A look extremely similar. In fact, they're of the same form. Okay. And this box square is the D'Alembert, which is given by two terms, the Laplacian and this del square by del t square. So this Laplacian, of course, involves three-dimensional derivatives, and then there's this time derivative. So together, okay, this is a four-dimensional derivative. All right, let me, start with this equation for V and A. You notice that V is linearly related to rho, just as A is linearly proportional to J. This linear dependence prompts us to do the following. So let us, let me in fact just concentrate on V. So A is vectors. Slightly more complicated, I have to remember to put an arrow. So since they look the same, so let me concentrate on D'Alembert acting on V, which is function of position and time, and that's equal to minus 1 over epsilon naught rho and R and T. And this linear dependence of V on rho says that we can write V linear proportion to this. So, and let me see. I want to have, this epsilon naught. So 1 over 4 pi epsilon naught. At first sight, it looks very complicated. I've made things more complicated than you would expect. But things simplified very soon, believe me. By introducing this Green's function technique, Green really had made a big contribution to physics. I think in 1930, when Albert Einstein went to visit Nottingham University, I think he said something like, by introducing the Green's function technique, George Green was years and years ahead of his time. Even Einstein was impressed. All right, so let me write things down first, then explain. Involves spatial integration and time integration. In terms, since it's linear proportional to rho, so this at rho at r prime at t prime. So you can think of r prime as the location of emission of a signal. The signal got propagated to the location r. The signal is emitted at time t prime, and the time at which the signal was received, r is t. And this propagation of signal is given by the Green's function, which depends upon r prime, t prime. Of course, we should take advantage of the fact that there's translational invariance in this problem. So that in fact, dependence on r and r prime in Green's function is given by the relative. And then time t relative to t prime. So this Green's function can be thought of as some kind of propagator. In fact, Richard Feynman, one of Schwinger's competitors, in fact, looked things in such a way that he interpreted this Green's function as some kind of propagator. So you may hear of the Feynman propagator for this theory and for that theory, etc. All right? So let's write V in this form in terms of the Green's function. Now to see how the Green's function, what kind of main conditions the Green's function have to satisfy. That's easy. Obviously, we want this V to obey this. So we want Laplacian minus 1 over c squared del square by del t square acting on this V R T that has to be equal to minus 1 over epsilon naught rho at R T. since now v, okay, is written in terms of Green's function that way, so let's have this D'Alembert act, okay, on all the whole thing, and notice that, okay, this derivatives refer to r coordinate, and this refer to time t, so that, well, the only place where r and t appears on the right side in the Green's function, r here, t here. So that, okay, this, okay, left-hand side would become, okay, so we have, okay, become 1 over 2 pi epsilon naught, 4 pi rather. Okay. Integration of r prime over t prime. Okay. This acts on that. So it's Laplacian. Okay. Acts on, okay, 1 over c squared, del squared by del t squared. Okay. Acting on the Green's function. Okay. Then times, okay, the charge density at r prime and then t prime. And we want this to be that for arbitrary rho. How is that possible? That's possible if what is, okay, inside, okay, this brace, this whole thing, okay, got to be given in terms of direct, okay, function. So that this got to be this 4 pi here, okay, and this minus sign, so this got to be minus, okay, 4 pi delta function of r minus r prime. Let me write it down first and explain. Okay. Then t minus t prime. Why? Because this is given by these two delta functions. Okay, 4 pi and 4 pi cancel. Okay. Then there's 1 over epsilon not here. There's a minus sign. Okay, this delta function, okay, would, okay, imply that, okay, upon integration of r prime, okay, r here, r prime here is converted into r. This delta function means in the integrand means that upon integration of t prime, that will convert t prime to t. So it's rho at t. So that, okay, this is, okay, the differential equation that the Green's function, okay, has to satisfy. And, okay, let me, okay, write it down, copy it down, okay, so that, okay, Laplacian minus 1 over c squared del squared by del t squared, acting on the Green's function, r minus r prime, t minus t prime, okay, that has to be equal to minus 4 pi delta of r plus r prime, t minus t prime. So we have to study this differential equation. And this is the differential equation for the 4-dimensional Green's function. 3-dimensional in the space apart, and then time dimension, an additional dimension. And, okay, this essentially is the function that George Green solved in 1839. Of course, in modern notation. At that time, the direct function was not yet introduced. Oh, I'm sorry. Hard to write things and, okay, talk and think at the same time. All right, this delta. Okay, before we tackle this problem, let's in fact tackle a slightly simpler problem. Well, how slightly simpler? Namely, let's talk about the 3-dimensional Green's function technique first. And I guess that in fact you might have encountered this, okay, in last semester. But if not, don't worry, I'm going to talk about it. Although I will be talking about it relatively quickly, since I assume that in fact you have encountered something like this, okay, in last semester, in 311. All right, so let us leave this aside, and now go on to talk about three-dimensional Green's function. The three-dimensional Green's function obeys, well, obviously. Let me put this minus sign to the other side. So it's minus Laplacian, the Green's function, okay, is equal to 4 pi delta of r minus r prime. To do that, okay, let me start with a function, okay, which I will denote by capital D of r minus r prime to be defined by. Oh, let me do the one-dimensional case first, but then I will generalize to three-dimensional. Right away. So x minus x prime defined to be, okay, 1 over 2 pi integration dk from minus infinity to infinity e to the I k x minus x prime, okay, then e to the minus epsilon, okay, magnitude k. And epsilon is positive. It's a constant. Okay. Let me start talking about this d function. Okay. Obviously, okay, this integration goes from minus infinity to infinity. And okay, you can, of course, okay, write the exponential function as the sum of two parts. One, the real part is cosine. The sine, the symmetric part is sine. Of course, in the symmetric part, with sine would integrate to zero because of the fact that the whole thing is symmetrical between the extension minus and plus k. So this effectively goes to cosine, just the real part, k of x minus x prime. And then I can rewrite this. Okay, instead of doing integration from minus infinity to infinity, it's symmetrical between the two, so that multiply by factor 2, so it's 1 over pi. Okay, then the integration is from 0 to infinity, e k of cosine k x minus x prime times this e to the minus epsilon. Okay, epsilon, as I said, is positive. Let me leave it as an exercise for you to show that this in fact is equal to 1 over pi epsilon over x minus x prime square plus epsilon square. So this is what d of x minus x prime is. Okay. And you can now integrate over dx minus x prime over x from minus infinity to infinity, with dx being given by this. And let me leave it as an exercise. Here, also exercise. Okay. This, in fact, is, guess what? 1. Now, let us, in fact now, specify that epsilon is not only positive, but it's infinitesimally small. So epsilon goes into 0 plus. So I'm interested in the limit. Epsilon goes to 0 plus. Okay. So that we have this. So I'm now interested in epsilon goes to 0 plus. It's positive, but it's very, very small. As small as okay. So what do we have? Well, what is that? What is d of x minus x prime in the limit that epsilon being positive, but very, very small? Well, what is that for the case x is not equal to x prime? For x not equal to x prime, this is finite. Since epsilon is small, okay, so that we can ignore it. So that it becomes epsilon over this is something finite. Epsilon goes to be infinitesimal small, so it goes to 0. 0 for x not equal to x prime. But how about x equals x prime? If x is equal to x prime, this is 0. Then you have here epsilon over epsilon squared, which goes to the 1 over epsilon. Epsilon goes to 0, then it goes to infinity. Not only that, okay, this function integrates to be 1. So what can that d function be? That d function, of course, satisfies all the requirements of a one-dimensional direct delta function. Direct delta function. Yeah, remember, direct delta function has this property and has this normalization property. So what I've done is that we have shown that the direct delta function can be written in integral form, which is this, and since epsilon eventually goes to is small, so I can formally ignore this. So it can be written as 1 over 2 pi integration of dk from minus k to plus infinity, e to the I k x minus x prime. And as I said, you may have encountered this integral representation of the direct one-dimensional direct delta function before. Well, maybe last semester in 311. But if not, there it is. Okay, next, we have a one-dimensional direct delta function. The integral form can be written as this. And obviously, the fourth, the three-dimensional direct delta function. Of course, can be written as, this for x dimension, then y, then z. All of them together. There will be 3 such factors, so it would be 1 over 2 pi q. And the integration goes over x, y, z. So dkx, dky, dkz. So let me just use dk vector notation. And then the exponential function combined very simply to be either I k dot r plus r prime. So this would be an integral form of 3-dimensional direct delta function. Next. All right. Now that I have an integral form for the 3-dimensional direct delta function, let me plug that into the right side of this 3-dimensional Green's function differential equation. So may I erase this? So this is 4 pi dot 1 over 2 pi cube dk, there are 3 integrations here, this vector, dkx, dky, dkz. And that's the d e to I k dot r minus r prime. And that is the minus Laplacian x on the 3-dimensional Green's function. Now, I have to solve this differential equation to get my 3-dimensional Green's function. Well, at this point, if you're so smart enough, you say, let me in fact write Green's function in the form of this. So that's the guess. But it's a good guess. So that it is given by what? Let me write this as 2 pi cube integral e to I k dot r minus r prime essentially, okay, the direct function, but now times a certain function of k. I do not know what it is. If I know, okay, then maybe I'm lucky. I can do this integration over k. Actually, it's not that hard to guess what this part of the integrand be in order for the Green's function in order to satisfy this. Well, we notice that if Green's function is of this form, the dependence on r and r prime rests on in the exponential. And imagine that. So this, of course, is nothing but grad that grad. And gradient, acts on this, of course, only act on this part of the integrand. So that when gradient acts on this, it brings this down ik. So the essentially, this Laplacian can be replaced by ik. And there are two of them. So that this effectively means that I can replace this by square of this, which is minus k squared. So that the guess is that this is in fact 1 over k squared. So this is 1 over k squared. Let's see what happens. Then when I take the derivative, so if this whole thing, so let me substitute into this 1 over k squared for the Green's function. Then this acting on this would bring down, as I said, minus k squared. Minus k squared cancel k squared, give me minus. Minus minus is plus. So that it would give just this. Oh, what happens to the 4 pi? Just a moment. Embarrassing. This a 4 pi problem? It should not be. Oh, okay. If not this, so maybe in fact I should put in the 4 pi here. Yeah, that's right. Okay, 4 pi. 4 pi. Okay. So now what do I have? So now, as I said, then I will. Okay, so this is I should have kept the 4 pi there. And then, as I said, when Green's function is given by this minus Laplacian acting on this would cancel this k squared and also give me a minus sign. Oh no, minus cancel. So indeed, that would give me what I have. We would cancel this. That would give me this direct data function with the same number factor, 4 pi over cube of 2 pi. So from this, we come to the conclusion that I can erase this now. The direct data function, Green's function, is equal to 4 pi over 2 pi cube integration dk of e to the minus plus. I'm sorry. I think I want to use plus. It doesn't matter. Since it's symmetrical between k minus k, but plus I k dot r minus r prime divided by k squared. Actually, this integration can be done relatively easily. Namely that, so we're interested in the k-space, the integration k-space, And let me pick this to be the k to z coordinate axis. Okay, and then I line this z axis in the k space to be along r minus r prime. So that when I have this is the origin, then let me take this to be k, and there's a relative angle between k, which you have to integrate over, and this direction r minus r prime. I've called this theta. So this is easy, and this you can use spherical coordinates. K squared dk, and then k goes from 0 to infinity. Okay, and then you have d phi, which will integrate to be 2 pi, and then you have d cosine theta, where theta is this angle. And this, of course, is nothing but k times unity of r minus r prime cosine theta. You can do the integration over theta, followed by integration over dk from 0 to infinity. Exercise. Show that Green's function is given by nothing but 1 over r minus r prime. And, if you like, we can check that that's true. So that our conclusion is that Green's function is given by just 1 over r minus r prime. That will solve the three-dimensional differential equation obeyed by the three-dimensional Green's function. All right, continue. Well, actually, let's see. Okay, let me, where I would like to go. Well, maybe I can continue here a little bit, and I can erase this now. I've done the integration. So our conclusion is that, minus Laplacian x on 1 over r minus r prime. Well, notice that in Green's function is always r relative r prime. On the right hand side, in the argument of that function, is also r minus r prime. So that without loss of generality, we can put r prime being 0 at the origin. So that let me in fact put this as the magnitude of r, that is equal to minus 4 pi direct delta function r. And the question is that correct? Let's check by something that you must have learned some time ago. And it turns out that what we are going to do would be used later on. So it's not complete waste of time to go over something you already learned. All right. And as usual, we will write the magnitude of the vector as r, as this one. So minus Laplacian with the 1 over r. Is it equal to 4? Whoop! Wait a minute. There's no minus. There's plus. I don't know why. Put in my sign myself. You want to check. All right. For r is not 0. Then let's check. Let's look at Laplacian acting on 1r. What's that equal to? And very soon we will have to conclude that in fact this question mark is just 4 pi times the three-dimensional direct delta function. Okay, let's check that. Let's find what it is. For r being not 0, then obviously I can now look at, since 1 over r depends only on the radial coordinate, so I can write down the Laplacian as 1 over r squared d by dr r squared d by dr. This is understood. D by dr is an operator x on everything standing to the right. So that in fact this d by dr x on that and that and that. So okay, very often you see people put a bracket there, but in fact okay, it's understood. All right. So let's check that. Okay. So so this now equals minus 1 over r squared d by dr r squared d by dr acting on 1 over r. For r not equal to 0, not the origin. That's simple. This is given by 1 over r squared of minus sign. R squared cancels r squared, so this is constant. D by dr acting on constant is 0. So that, minus Laplacian acting on 1 over r is equal to 0 for r not equal to 0. That looks good. Next, how about they look at r goes to 0? Or then, this 1 over r diverges. It's not meaningful. So that what we should do is that, in fact, let's take this, integrate over a sphere with a very, very small radius around the origin. So let's do that. So integrate over r around with radius r. Eventually, let r goes to 0. All right, what's that? Integration over r of minus Laplacian 1 over r. Oh, that can be done. This is minus, this is nothing but divergence of gradient. So this is minus, dr. And now this, very often we use the notation, the volume integration, d tau, around for a small sphere. And this is divergence, divergence of gradient acting on 1 over r. Of course, it's nothing but 1 minus r squared. Gradient acting on this unit of r, of course, is nothing but the unit vector of r. And now, obviously, this volume integral of a divergence. We can now use Gauss theorem to convert it into a surface integration. So this minus is plus, so this becomes dA dot, this 1 over r squared r hat. So this is nothing but, this dA has radius r squared, so d phi d sine theta. Well, I can use cosine theta. Then 1 over r squared around for the surface of this small sphere. R squared cancel. So this integration, this gives me 2, this gives me 2 pi, so it's equal to 4 pi. So that we see that, this, acted on by the Laplacian would be 0, and r equals not 0. But, it also has the property that, this integrating over volume, is equal to 4 pi. So now it is abundantly clear that this is nothing but 4 pi derivative function. So that when you integrate over the volume, it gives you this gives you 1, so it leaves you with 4 pi. Whereas when r is not 0, this is 0. as said, because delta function consistent with the fact that delta function is 0 at argument being non-zero. So that indeed this is correct. So that's the three-dimensional case. Now, wow, okay, it takes time. Let's go on to talk about the four-dimensional case. And, okay, we are ready. Look at this problem. So this is what I would like to tackle. And to start with, let me make use of the fact that I know what this looks like in integral form. This can be written as 1 over 2 pi d omega from minus infinity to infinity. Let me use omega as integration variable for good reason. Time always goes with omega, just as r goes with k based on number. And I will use this either minus I omega t minus t prime. Okay? And what I would like to do is the following. I would like to write this four-dimensional Green's function in a form so that it will look like this one, involving an integration over omega. So let me write this as this, namely that 1 over 2 pi integration over omega from minus infinity to plus infinity e to the minus I omega t minus t prime. The time dependence appears here, but the R dependence appears as a separate factor. And let me call this Green's function, and it depends upon omega. Green sub omega dependent upon R minus R prime. Let me put it in that form. So if I can work out what G sub omega is, then I can maybe plug it back into this integral to a one-dimensional integration and get my four-dimensional Green's function. And that's what I want. All right, so let me write it in that form. Okay. If I write the four-dimensional Green's function in this form, now let me take a look at the left-hand side. I have Laplacian x on this. Okay, of course, that will go through this part of the integral. This involves node R. Okay, so that the left-hand side would become 1 over 2 pi integration of omega minus infinity to infinity, and this will only act on this. So let me write this down. So I have Laplacian x on this part which depends upon R minus R prime. How about this? This x on the Green's function, t of course appears in exponent. So when I integrate, when I take derivative, each time I will bring down a factor of minus I omega. There are two of them. So that will be minus omega squared. So that would be minus minus is plus. I hope that's correct. 1 over c squared omega squared. And the rest is here. Minus I omega t minus t prime. That would be the left-hand side. And this is supposed to be that. All right. Supposed to be this. And let me make sure that I have not made any sign mistakes, etc. So let's see. Correct. All right. And so that, I now, let me make sure. So let me copy this down. Okay. So it's equal to minus 4 pi 3-dimensional delta functions times this 1 over 2 pi integration of omega e to the minus I omega t minus t pi from minus infinity to infinity. Now, okay, how do I get this? There's already this vector is there. So that if I have, okay, now I can obviously equate this with that factor. Then this part would give me back this part. So that I arrive at, okay, a 3-dimensional differential equation, which looks like, okay, the original 3-dimensional Green's function equation. So look at this. So, okay, now I want this to give me that. Let me copy down here. There's a minus sign. So if I put the minus sign to the other side, minus Laplacian plus omega square over c square times Green's function sub omega, it depends on omega, that is equal to, let's see, this 4 pi delta function r minus r prime. If you compare the original 3-dimensional Green's function equation with my g sub omega, they look the same, except that now, in fact, okay, this is an extra term, okay, in the operator. So that in fact, okay, g sub omega, okay, would go to, okay, the Green's function that I've solved, which is 1 over, okay, r minus r prime magnitude. In the limit, in the static limit, omega goes to 0. That's one thing that we know. All right. So, what should we do next? Okay. What we should do is, okay, of course, tackle this equation. And let's see, I can erase this now because, okay, but I have to be careful. So that I want to keep this. So once I've solved for, okay, g sub omega, okay, I can plug into here. Then, okay, the 4-dimensional Green's function that I want is just given this. So let me keep this here. But then this I cannot erase. I need backward space. All right. Yes. To start with, obviously, okay, on the right-hand side, it's always r relative to r prime. And on the left-hand side, also r minus r prime in argument. So again, without loss of generality, let me set r prime being the origin of the coordinate system. So I want to solve minus Laplacian plus, okay, omega square over c square of Green's function, so omega r, that's equal to 4 pi delta function of r. Let me now solve this equation, okay, for r not 0, not the origin. In that case, then of course, the right side will be 0. have, okay, there I have Laplacian plus omega squared c squared, this Green's function r, the 0, for the case r not the origin. But we know that, in fact, on the right hand side, this equation involves this delta function. Okay. And okay, we can take into account the existence of this singularity at the origin by using the method that we did before. Namely, take this equation, integrate over a small sphere surrounding R. Let's do that, actually, before we go on to solve this equation at R not 0. All right, so here, let's integrate over a small sphere. R as R goes to 0. Okay? I'm going to show you later that, in fact, when you do one integration over a sphere, as the sphere shrinks to 0, this term, in fact, doesn't contribute. I show you, I prove it. Okay? The reason being that, in fact, as R goes to 0, we will show that this goes like 1 over R. Okay, so this is 1 over R, this is a constant, so that this piece, in integral, will go like 1 over R, but then you have a sphere, d goes as dr squared over dr. So that is R goes to 0, that would shrinks to 0. So that, in fact, this term doesn't contribute to this Fourier integration. And I have to check. Need to check this. Of course, it's correct. Otherwise, I will not be telling you. All right. Integrate over this. Okay. Now, what do I have? Then, the right-hand side, obviously, when you integrate over a sphere, this delta function gives you 1. So the right-hand side was equal to 4 pi. How about left-hand side? What do we have? So we have, what we have is that, this goes away. So we have, minus, have volume integration of volume over small sphere. Only this term contributes, which is Laplacian, which is gradient, divergence of gradient over this G omega R. Okay. Let's see. Next. What do I want to solve? Okay. Let's see. So this one again, I make use of Gauss theorem. So this is minus dA for the surface of this small sphere. This divergence. This volume integral of divergence is this area integral of this grad G omega of R. All right, and this one obviously A, of course, is points along the radial direction. dA, that is nothing but dA, points along radial direction. So that takes out in the gradient, just d by dr. So that we have, let me continue here. Integration over the surface goes like R squared. Then 4 pi coming from the integration over the angles. The solid angle is 4 pi. So continue here. So minus 4 pi R squared d by dr x on this Green's function, this, for r goes to 0. And we are told that that should be equal to 4 pi. It's 4 pi. So there's a boundary condition that this Green's function, let me write it down here. D by dr acting on the Green's function, which depends on omega, as r goes to 0, got to be equal to, let's see, got to be 4 pi cancel minus 1 over r squared, isn't it? So we have this boundary condition. And let me make sure that I've not missed any term with a sign, things like this. That's the that's the minus sign. Let me in fact, I didn't make a mistake at all. So that, let me now go over this part of the thing. May I erase this? Do the calculation here. So that the very fact that there's this delta function in this Green's function, tells me that there is a boundary condition that are got to be satisfied, namely this one. So that let me put the other side. So I want to need boundary condition. Given by minus r squared d by dr acting on this Green's function, has to be equal to 1. Have we got the sign right? Minus is already there. R squared, yes. As r goes to 0. So this is the boundary condition that we have to make use of. Later. By this point, let me now solve. Come back to this part of the blackboard. This equation at r not including the origin. So this is done. I've got it down already. The condition, the boundary condition comes from here. So let me erase. Things sometimes might look complicated, but once you get used to it, once you know how to tackle the problem, step by step, in fact, it's not that bad. And in any case, it's a nice technique to learn. All right. So I want to solve this difference equation. And r not equal 0. Good. And to do that, I know already, and also I have to check that this is correct. And I know that in the static case, g of r goes like 1 over r. So let me in fact now write this g sub omega of r equals to 1 over r, which would be the result for the static case when omega is 0. But now multiply function g sub omega of r. And in that case, then what happens? Again, so this is equation for this equation. It helps to use spherical coordinates. So that the Laplacian is nothing but 1 over r squared d by dr, r squared d by dr. So d by dr acts on everything standing to its right, and this d by dr also is an operator, acts on everything stand to its right. All right. So let me take a look. Take a look at this part first, and this, so that I have let me take a look at the first term. So G now is, look at this, is of this one. Now I have R squared d by dr acting on 1 over R G, small g sub omega of R. And what is that? So this is an operator, x on everything to this right. So that means x on this, 1 over R, as well as this. So it's equal to R squared. When it x on, okay, so there are g omega sub R. When it x on this R, then it gives you, okay, minus 1 over R squared. Okay, then it can act on this, so that 1 over R d by dr x on small g sub omega R. After that, okay, we still have to, okay, act by another d by dr, then multiply by 1 over R squared for this Laplacian. Okay, so then now 1 over R squared d by dr acting on others would be equal to, all right, acting on this term. So this can, okay, let me copy that down. Oop. Yes. Okay. So let me separate this. So this R squared times R. So there's one factor of R. May I use this? And for this one is R squared cancel R squared. Okay, that is minus 1. So that's minus G. So then now I have this extra operator, x on this. So that, okay, this term give me 1 over R squared d by dr acting on small g omega R. This term. Then this acts on that. Okay. D by dr can act on this one. Okay. So this gives rise to two terms. When d by dr acts on R, there will be 1. So I'm left with 1 over R squared. And this dg omega by dr. That's when d by dr acts on this. But d by dr can act on this one. In that case, then this r cancels with 1 factor here, with plus 1 over r. Then e squared by dr squared g sub omega. Oh, this should be a minus sign, please. That is very strange that I do not have a minus sign. Okay, let's see. This 2 should cancel. Let's see. Where did I make a mistake? And this one, oh, there must be a minus sign. Let me take a. So I only get this result. Yeah, somehow, okay. This is that. Is there a minus sign? Yeah. This sign this should cancel. So these two terms should cancel. So one of the terms got to have a minus sign. Okay. Oh, there's a minus sign here. I just erased. There's minus sign here. Okay, somehow. Okay, I got it wrong. Because, okay, d by dr on this one, there's a minus sign. So in fact, so that I have, okay, let's see. So that I have, okay, so that this term, okay, is one of them is minus, okay, minus. There's a minus sign. Comes from this minus sign. 1 over R squared, minus sign, d by dr act on this. So indeed, hallelujah, this cancels that. So that, oh, it's taking longer than I thought. Sorry. So that I come to the conclusion that, okay, where am I? This thing, okay, act on this one, just give me that. So that I have, okay, so that I have, this becomes, this equation becomes, I thought space here goes all the way here. becomes, let me copy it down, okay, the result, and you can see dr squared plus, okay, it's here, okay, this is the only term that's left, okay, plus omega squared over c squared times the small g omega r equals 0. And I can explain. Okay. All right. This give me essentially this term. Okay. D squared by dr squared. That's 1 over r. But this 1 over r is there in g. So if I multiply r, since r is not 0, I can do that. So I get this. That's correct. Now this is simple. Okay, second order differential equations. Solution is immediate. G omega of r is equal to up to a constant factor is e to the, okay, plus or minus I omega over c r. If I am not, okay, mistaken. Correct. Oh, wait. Oh, that's right. Okay. That's the small g. And now this big G is that what I want. G is omega r is equal to 1 over r times this. This is a constant, okay, factor that I have to determine. E plus minus I omega over c r. Almost done. Okay. And now, what I want? I want, first of all, check that this is correct. Look at this. When r is small, indeed equals to 1 over r. When r is small, this can be neglected. So this is correct. So since this is correct, so that's why, in fact, we really could forget about when we integrate this equation. We can ignore this term. So I have testified that. Next, okay, now that I have solved for the big G's omega, I plug it in here to get my 4-dimensional Green's function. And now I can erase all this. So a lot of tedious calculations, although not uninteresting in a way. Okay. So that my 4-dimensional Green's function. Okay, in fact I have this, and this is equal to 1 over 2 pi integration over omega from minus infinity to infinity e to minus I omega of t minus t prime, and this we get this is for the argument r. Of course, in place of r, I can always now substitute r minus r prime. So that I have 1 over r minus r prime, replacing this 1 over r, times constant c, times e to the plus or minus I omega over c times r minus r prime. Is that. And what's next? I hate the clock. Okay. Oh, actually, before I do that, actually, if this is what we found up to this constant, I can in fact right away, make sure I use the boundary condition here. Okay. So that as r goes to 0, d by dr can add on here, and can on here. But when it acts on this, then we bring down such a factor, omega over c. Then there are 1 over r, but that multiplied by r squared. As r goes 0, that would be 0. So in fact, all we have to keep is the d by dr acting on this r. So now we have minus r squared, d by dr acts on this r, okay, will give me minus 1 over r squared, then the constant e to the plus or minus I omega over c, okay, r, okay, and take the r goes to 0 limit, that should be 1. Look, see, this is 1. When r goes to 0, this is 1. So c is just 1. After can we use of the boundary condition? Good? We're getting there. So that. Okay. So let me recopy this. So this is equal to 1 over 2 pi. Let me pull out this r minus r prime term, and then I'm left with integration over omega minus omega e to the minus I omega. Okay. Then plus, let's say, okay, this is okay, plus or minus, okay, this r minus r prime over c, I omega is taken outside already for this, then this one, plus, so this minus t minus t prime. This, okay, of course, it's nothing but the direct delta function in one dimension. Okay, I've managed. It's here. So that okay, if you compare the form of the one dimensional direct delta function given here for this, compared with this, then you find out that this is nothing but the direct delta function of okay. Let's see. So this got to be 0. So it's plus or minus r minus r prime divided by c minus t plus t prime. Almost done. Okay, give me 5 more minutes. All right, let's wrap it up. Okay, so it looks like we have two solutions. One with plus sign here, one is minus sign here. Let's take a look at those two cases. I can now erase this. Okay, let me consider this. Okay, delta, plus case, then minus case. Plus case says that r was r prime. Okay, give me this. Okay, minus t plus t prime. This delta function says that this is equal to that. This delta function for the plus case says that the argument of the delta function is 0. So that means that this is 0. That tells you that t is equal to t prime. Oops. I'm sorry. Now so the plus case, still right? Plus case here is t prime. Right. Okay. So the t plus r plus r prime over c. Remember, t prime is the emission time. T is the observation time. The observation time for this plus case is the emission time plus this one. So the observation after emission. So this is consistent with causality. And by the way, this is nothing but the time it takes light, during the speed of light c, to go from r prime to r. Okay. So this, we would call this the retarded time. T sub retarded. And this result is consistent was what we expect. Okay, effect after cause. Whereas the minus case, okay, we say that actually t will be equal to t point minus that. So this we say that okay, it is effect before cause. That's inconsistent with our physical intuition. So this okay, case must be dropped because of for physical reasons. So that okay, we have okay, what we have is okay, this is the solution. And next time we come back to this, okay, and finish up the whole calculation. Let's stop here.